All right, how's everyone feeling today?
Totally awesome, sir.
All right, that's what I like to hear. So today we're going on to our next unit on vector quantities. And the first question is, how can we use vector units or unit vectors to express vector quantities? Unit vectors are known as I, j, and k vectors, or sometimes it's x, y, and z unit vectors. We'll be using the traditional ijk unit vectors, and it's just a sophisticated way of communicating what a vector quantity is. So to start off, let's do a little blast from the past problem where you have to find the resultant of two concurrent forces. Two forces acting on the same point at the same time. So, sketch out the problem. There's a 40 Newton force acting at an angle of 30 degrees. So from the positive x-axis over to here, that would be 30 degrees. And there's a 20 Newton force acting on the object at 60 degrees. So from the positive x-axis all the way up to there would be 60 degrees. So I want you to work on finding one single force that would have the same effect on the object as those two forces acting simultaneously. The name of that one force that would do the same job as those two acting simultaneously is called the resultant force. So find the resultant force. Let me see if I can make that diagram a little bigger. The first way I want to review solving this problem is by drawing a second head-to-tail diagram. If you have a vector, a vector is just a special name for an arrow. An arrow is called a vector. It's used to represent a vector quantity. Vector quantities have size and direction, or you could say magnitude and direction. Arrows are perfect for representing vector quantities. A specialized cool name for the arrows used to represent vector quantities? Vectors. The side of the vector that has the arrowhead is usually referred to as the head of the vector. The side that doesn't have the arrowhead is usually referred to as the tail of the vector. The diagram shown here, I personally call the real scenario diagram. It shows how it's really happening. You have an object right here, and it's being tugged this way, and it's being tugged in this direction, and we're looking for one force that would do the job of those two working simultaneously together. This diagram could also be called a free body diagram, where this point was freed up from more, sophisticated, real-world diagram, so that all the forces acting on that point are shown. What I want to do is draw a head-to-tail diagram. So I draw the first vector. I'm just sketching it out. It was up 30 degrees. And what was the magnitude? 40 newtons? I'm carrying along 3 sig figs. So down here would be the tail of that vector. Up here would be the head of that vector. Now, up on the head of that vector, I want to draw the second vector. But I want it going in the same direction it was going in the original free body diagram. So up at the head, I draw another reference line. Sometimes people like to put a little coordinate system. And I know on that coordinate system, I have to measure up 60 degrees this time, yes? And I'm just sketching it out here. What was the magnitude of that next vector? 20 newtons. So this here is a head to tail diagram. Because the head of the first vector is touching the tail of the second vector. Sometimes solving the problem this way is called solving graphically. Not that you're drawing like an XY graph, but you're just drawing out the vectors. Sometimes people do it with a scale diagram. Now, the resultant vector would go from the starting point, and the resultant vector, when doing a head-to-tail diagram, always headbutts the last vector added. Now the physics is done, and it's simply a math problem. Unfortunately, it's not the easiest of math problems because it's not a right triangle. If we call this first side the 40 Newton vector A, and this second side over here, vector B, let me use lowercase. And the resultant force is side C. You can't just use Pythagorean theorem because it's not a right triangle. You have to use a expanded version of Pythagorean theorem. Can anyone read your physics teacher's mind?
Law of cosine.
Law of cosines. So if you write out the law of cosines, c squared equals a squared plus b squared plus 2 times a times b times capital C.
I think it's minus.
Whoop, minus.
Minus.
And then we could plug in the values. C squared equals a squared. Well, the magnitude of A was 40 newtons. Squared plus B, and the magnitude of vector B was 20 newtons. Squared minus 2 times A times B times the cosine of angle C. Well, commonly the practice is the sides of the triangle are indicated with lowercase letters, and the corresponding opposite angles are signified with uppercase levels. So for example, if this here was side B, this angle right in here would be capital B. And if this side over here, the resultant, was side C, this angle opposite of that would be capital C. And if this side over here was A, the side opposite of that over here would be capital A. So we need this capital C angle right here. It's not directly obvious, but we could definitely figure it out. Let's just zone in here a little closer. I know I have a straight line here. If from here to here is 60 degrees, what would this angle over here be? Wah, 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 wah. Those would be supplementary angles. So if that there is 60, what is this big angle over here? 120 degrees, yes? And then over here, notice I have a horizontal line and here's a horizontal line. If this is 30 degrees here, this angle here, it's also called, it's also 30 degrees. That's the alternate interior angle. So that there would be 30 degrees. So if this little angle here is 30 and that little angle there is 30, now we could go back and figure out what capital C angle is. This whole thing right there. No. And it would be 120 plus 30 degrees. So I can come back over here, and it would be cosine of 150 degrees. Now I have to plug and chug. So did anyone happen to crunch out that resultant? 58.2? Notice that's carrying 3 sig figs as the original data had. But before you rounded, what was the value? Just for
58.18.
No, that's good. So this, of course, is your answer. And if you were reporting the magnitude, you would report that. However, if you needed to use that to do more calculations, you would want to use this one here. You have to carry a few extra digits to preserve the precision of the original measurements. So it's a little bit tricky. To report the answer, you round to the correct number of sig figs. But if you're going to use that calculation to keep on going, you would carry along the few extra digits. So the good news is we found the magnitude of the resultant. A force of 58.2 newtons would do the same job as those 2 original forces. But are we done? What else would we need to find, David?
The measure of the degree.
Yes, the measure of the degree. We want to indicate the direction. So coming back down, the standard thing to do is to indicate what the direction is relative to the positive x-axis. Sometimes I refer to that as the at angle. Like at the beginning I said at 30 degrees and the other one was at 60 degrees. Well, I want to know what's the at angle of the resultant. I want to find this angle right here between the positive x-axis and the resultant. But in order to do that, I'm going to have to find angle B first. Capital angle, capital B. I can't just use SOHCAHTOA because it's not a right triangle. So what's a poor physicist to do to get capital B?
You can use the law of sines.
You have to use the law of sines. So let me make room up here. Law of sines says
Sine A over A equals sine B over B.
sine of A over A equals sine of B over B equals the sine of C over C. But you usually don't use all three. You use the two, one of which you have the known values and one of which is unknown. In this case, I'm going to use these two right here. I don't know capital B, that's what I want. So the sine of capital B over side B, which is 20 newtons, equals the sine of capital C. I do know capital C, I figured that out before. That's the 150 degrees. Over side C, which I figured out, but again, I want to carry along the extra digits now because I'm doing a further calculation. And then when I solve for angle B, what does that come out to be?
9.896.
9.896 degrees. And then what do I have to do with that?
You add it to 30.
You add it to 30. So my angle B over here, or my at angle for the answer would be 30 degrees plus 9.896 degrees. So the angle would be 39.896 degrees. But now I want to round to 3 sig figs, so I would say 39.9 degrees.
Mr. Slinsky,
Yeah,
how do you know it's 3 sig figs?
all the original data points were given with 3 sig figs.
Okay.
So voila, I found my answer. What was the magnitude? 58.2 newtons at, and what was the angle? 39.9 degrees. That was a little blast from the past, the head to tail method. But that's not the sophisticated way of finding the resultant.
It's not.
That was so hard.
Can anyone read your physics teacher's mind, Manav?
Well, I'm not. I did the component method.
Yeah. The sophisticated way, as Manav said, is to use what's known as the component method,
What's that?
where you break each vector down into its perpendicular components. You add up all the horizontal components, get the horizontal resultant. You add up all the vertical components to get the vertical resultant,
To make a new triangle.
and you make a new triangle, which is going to be a right triangle,
With hypotenuse.
and you find the resultant of those two mini resultants.
That's easy.
So that's the sophisticated way of solving the problem. So let's quickly run through that. You draw each vector by itself. So what was that first vector? 60 newtons?
40 newtons
40 newtons.
40 newtons.
at 30 degrees.
And you draw the second all by itself.
40 newtons at 60 degrees.
And for each one, you create a vector triangle where the components are in head to tail form, because the resultant of the components is the original vector. So if I was playing the game over here, I would put my pen down at the tail of the original 40 Newton, and I would ask myself, is that 40 Newton force sort of going to the left or to the right?
Did I?
To the right. So I draw a vector going to the right. And then keeping my pen there, is that original 40 Newton vector sort of going up or down? Up. Those two arrows represent the components, or the perpendicular components of the 40 Newton. They're at a right angle. They're in head to tail form, so you know their resultant is equal to the 40 Newtons. And now, since this is a right angle in that corner right there, you could use SOHCAHTOA to find the magnitude of the two legs. So, what's the magnitude of that horizontal component down here?
Sorry, did I charge it?
Yes.
Thank you. Bye.
That would simply be, you could write it out. Cosine equals adjacent over hypotenuse, put in the values, but you get fast at this. You recognize that, that leg right there, that's just going to be 40 newtons times the cosine of 30.
Approximately.
This one over here is going to be 40 newtons times the sine of 30. If you don't see it, write out SOHCAHTOA, sine equals opposite over hypotenuse, plug in the values, rearrange. But this work you don't even have to show. This is like quick, grunt work. So could anyone tell me the horizontal component of that vector?
Approximately 34.6 newtons.
34.6, but we want to carry a few extra digits.
641.
641 newtons. And then what about the vertical component?
17.320.
I got 20.
I got 20.
I wrote that as a wrong number. Sounds good.
Yeah, this one, yeah, it's one.
And then for the other vector, I want to create a little vector triangle. And what's the horizontal component?
10 newtons.
10 newtons?
Yeah.
And what's the vertical component?
17.321.
And now I could find the sum of all the forces in the x direction, which would be the 34.641 newtons plus the 10 newtons. And when I add those up, Those are easy enough to add. I get 44.641 newtons. Then I could find the sum of all the forces in the y direction. So I add up 20 newtons plus 17.321 newtons. And easy enough again to add up. I get 37.321 newtons. And then once you know the little mini resultant, the one of all the horizontals and the one of all the verticals, then what do you do with those two?
Make another triangle.
You make another triangle and you find their resultant, but it's going to be pretty easy because they're at a right angle to each other.
Use Pythagorean theorem.
And you can use Pythagorean theorem. So how much was that horizontal component?
44.641 newtons.
Head to tail, how much was that vertical one?
37.321 newtons.
I sketched those two out head to tail. I draw the resultant. And then I could find my vector C. By what means?
Pythagorean theorem.
Hi.
Pythagoras would be proud.
Who? Okay. Right. Sapphic? The guidance at the end of the period. And if you use Pythag, C squared equals A squared plus B squared, what do you end up getting?
58.186 newtons.
And now 58 point what?
186 newtons.
186 newtons. And if we round to 3 sig figs, what do we get?
58.2 newtons.
Is that what we got before?
Yeah.
Excellent. And how could we get the at angle?
Find the inverse tangent of the vertical over the horizontal.
Yeah. And if we do that,
We get 39.896 degrees.
and rounding to 3 sig figs,
39.9 degrees.
and how does that compare?
It's the same.
So, what we're going to see is that there's a more sophisticated way of writing out these components. And the more sophisticated way is using these baby vectors called unit vectors. Now, we took a little longer to do the original problem, the two methods, so we didn't quite get to the unit vectors, but that's okay. We set ourselves up for success for Monday. So we'll have a part 2 to this lesson on Monday, and that was great. Thank you, guys.